This is a review of the sample final for BQUA 2811. Number 1. The life expectancy of computer terminals is normally distributed with a mean of 4 years and a standard deviation of 10 months. A. What is the probability that a randomly selected terminal will last more than 5 years? So the first thing we have to recognize is that the mean is given in years and the standard deviation is given in months. So we've got to convert them to the same units. Let's say for simplicity we'll convert them to months. So if the mean is 4 years, 4 times 12, that's 48 months. So we have a mean of 48 months and a standard deviation of 10 months. What is the probability that a randomly selected terminal will last more than 5 years? So it's normally distributed. This is a single item, so we're talking about a normal distribution with mean 4 years and 48 months. If we want to know the probability that it lasts more than 5 years, that is the probability that x is greater than 5 years would be 5 times 12 is 60 months. The probability that x is greater than 60 months. Now, since we're talking about greater than, the norm dist will give the probability that it's less than or equal to, so we have to subtract it from 1. So our answer is going to be 1 minus norm dist of, we're looking at 60 months. The mean is 48 months. Standard deviation is 10. And when using the norm dist, we'll always put in true. So our answer is 0.11507, 11%, 11.5% probability that it will last more than 5 years. Again, because we're looking for the probability that it's greater than 60 months, we have to subtract norm dist from 1. In a certain large company, a system, a certain shipment of terminals of a certain shipment of terminals, 25 lasted more than 5 years. Approximately how many terminals did they have altogether? So if there's an 11% probability, if there's an 11.5% probability that it lasts more than 5 years, then what we're saying is that 11% of what? 0.115 times what is equal to 25. Again, we're saying 11% of what is equal to 25. So x is equal to 25 divided by 0.115, but rather than using the 0.115, let's copy it from the exact number, and our answer is going to be 217.25. C. What percentage of terminals will last between 4 and 5 years? Again, so now we're talking again about the norm dist. 4 and 5 years is 48 months to 60 months. So we've got the probability that x is between 48 months and and 60 months. All right, let's fix that. So x is between 48 and 60 months. That's going to be equal to norm dist for the higher one. The higher one is 60. Mean is 48. Standard deviation is 10. True. Minus norm dist of the lower one. That's 48. Again, 60, 10, and true. All right, 0.76. probability that it's between 4 years and 5 years, between 48 months and 60 months, and there we have 0.76. Let me just see if we got those numbers right. It's the mean was, this is a mistake, the mean was not 60, the mean was 48. So there we go, and our answer is 0.38. Again, what we're looking at is 60 months minus 48 months, so it's 60, and then the mean in standard deviation is 4810 minus 48 months, so it's 48, and again the mean and the standard deviation is 4810, and true. Okay, so here's our answer, 0.38. What is the range of years of the middle 90%? So the middle 90%, again, we should know the probabilities for the middle 90%, but just in case we don't, we can calculate it. So we're looking for the middle 90%. The middle 90%. The middle 90% has 5% below it and 5% above it. So the z-value associated with the middle 90% is going to have 5% below it and 5% above it. So if I want the lower value, I'm going to place 0.05 into norm inv, because this is minus x. Well, that's not, this is the negative one. Let's not call it minus x. This is the lower side. And the upper side, so let's call it from x1 to x2. So x1 is going to be norm inv, with 0.05% is below norm inv, so the probability is 0.05, and the mean is again 48, standard deviation is 10, and so on the lower side it's 31.55 months. 2, that's x1, 2, and now x2. What percentage is below x2? Below x2, I've got, below x2 I've got 95%. The 5 plus the 90, so below x2 I have 95%. So that's going to be norm inv of 0.95, and it's again the mean is 48 and the standard deviation is 10. So we have from 31.55, this is in terms of months, this is all months. So the middle 90% will be from 31.55 months until 64.44 months. Next, E. If the manufacturer guarantees that the terminals, if the manufacturer guarantees the terminals for 3 years, what percentage of terminals will be replaced? That means any terminal that breaks before 3 years will be replaced. In other words, we're talking about the probability that x is less than 3 years. 3 years is 3 times 12, 36 months. Again, we're doing everything in terms of months, so it's going to be replaced if it's less than 3 years. So that's very simple. Let's just norm dist. 36, 48, 10, true. And again, that's now the answer because we're talking about less than, so to the left side, norm dist gives you the amount that's less than, so we don't have to subtract it from 1 or do any other arithmetic on that. Next, if a sample of 9 terminals is taken, what's the probability that the mean of these 9 terminals is between 4 and 5 years? Okay, so if you're talking about the mean of the sample, now you're talking about a probability. Whoops, keeps moving. We're talking about a probability about x bar. Remember, that's the sampling distribution of the mean. So if we're talking about a probability about x bar, in other words, we're saying what is the probability, not that x is between 4 years and 5 years like we did before, but the probability that x bar is between 4 years. 4 years is 48 months, and now we're talking about x bar less than or equal to 5 years. Right now, this is going to be similar to what we did before, except that we have to use the sampling error in calculating this, or in other words, the sample the standard deviation of x bar rather than the standard deviation of x. So the standard error, standard deviation of x bar, we have to use it again. Why? Because we're getting a probability about x bar. The standard deviation of x bar, also known as the standard error, and that's equal to sigma over the square root of n, sigma over the square root of n, okay, so in our case we're talking about sigma is 10, that's 10 months, and the square root of n is 9 because we had a sample of 9 terminals, so the square root of 9, and our standard error is 3.33. So we're going to do the same calculation we did before, except using the standard error. So that's going to be norm dist 60, 48. Okay, but now we're using the standard error of the standard deviation of x bar instead of the standard deviation of x. True. Minus norm dist 48. And here is our answer, 0.49. So we're recognizing that the probability that you're within 48, 4 years and 5 years is much, much larger if you're talking about taking the mean of a sample of size 9 as compared to the a single item. Single item, the probability was 38%. And for the mean of 9 items, the probability that it's between 4 and 5 years is over close to 50%, 49.9%, and that's understandable because, as we said, the larger the sample size, when I take a sample, the values tend more toward the center. Now, I could have done this whole thing all at once without calculating the standard error separately. Let's just see how I would do that. It's the same calculation. Norm dist 60, 48, I'm sorry, 60, okay. Now, instead of putting in 10, we're putting in the standard error, but we could calculate the standard error right in this norm dist function, so I'm going to say 10 over the square root, 10 over the square root of 9, true, minus norm dist 48, 10 over the square root of 9, true, we did the same calculation as we did before, but we calculated the standard error right in the norm dist function. Number 2. We're interested in estimating the average amount a family of 4 spends on a vacation in Niagara Falls. Suppose a sample of 64 families, so n equals 64. Vacation in Niagara Falls resulted in a sample mean of 252.45, so that's x bar. It is known that the standard deviation of the population is 7450. That's sigma. Very important to recognize. When the population standard deviation of known is known, that's sigma. When the population standard deviation is known, we're going to use the norm dist or the z distribution. When the population is when the standard deviation of the population is not known, we're going to use t. We'll see that later. But so far, since the standard deviation of the population is known, we're going to use the z distribution. Compute the standard error of the mean. So we already know that the standard error of the mean is sigma over the square root of n. That's sigma over the square root of n. So it is 64. No, sigma. 74.5 divided by the square root of 64, standard error of the mean. Next, will the sampling distribution of the mean, that's the distribution of x bar, necessarily be normally distributed? Why not? Now, again, there are 2 conditions under which the x bar will be normally distributed. Either if x is normally distributed, then no matter the size of the sample, x bar will be normally distributed, or if the sample size is large, which we consider to be at least 30, then x bar will be normally distributed whether or not x is normally distributed. In this case, the sample size is 64, therefore the answer is yes, x bar is normal or normally distributed. And how do we know that? Because n is large, and in this case that means n is greater than or equal to 30. For a 99% confidence interval, find the margin of error. The margin of error is the amount that you add and subtract to x bar in order to get the confidence interval. We know that since we're using the z distribution, and the reason again that we're using the z distribution is because the standard deviation of the population is known, the margin of error, let's call that E, is going to be equal to the appropriate z times the standard error. That's, or another way of saying that is z times sigma over the square root of n. So the margin of error is z sigma over the square root of n. Since sigma over the square root of n is the standard error, it's really z times the standard error. Think of it either way. So that's going to be z. Now what's the z value that we're using? So for a 99% confidence interval, what is the z value? We should know by heart the z values for 90%, 1.645, 95%, 1.96, 99%, 2.576. If you don't know that by heart, then you can calculate it in the same way that we calculated the 90% value in the previous problem. So, z, 2.576. Again, that's the z value for a 99% confidence interval. 2.576 times sigma over the square root of n. I can plug in sigma over the square root of n. Sigma is 74.5 over the square root of 64. Or more simply, I can say it's equal to z 2.576 times the standard error, which we've already calculated before. And there you have it. Okay, so that is the margin of error. So what's the 99% confidence interval? The 99% confidence interval is x bar minus the margin of error to x bar plus the margin of error. 228 to 276. And finally, for part E, suppose you want the 99% and would have a margin of error of 10. Our margin of error was 23. So if we wanted to have a margin of error of 10, that means that the sample size will be able to be what? I want it to be 10. It was 23. Will the sample size be lower or higher than the 64? Well, the smaller you want the margin of error to be for the given level of confidence, the larger the sample size is going to be. We have a formula for sample size, and our formula for sample size is n equals z sigma over n squared. Z times sigma over n, the whole thing squared. So that will be equal to, what's z? Again, since we're still looking for the 99% confidence interval, that's 2.576 times sigma is 74.5 over, and that shouldn't be over e, that should be over e squared. That should be over e squared. We'll fix that in a second. The e is 10 squared. So there's our answer, 368. Again, let me fix this formula. That's not z sigma over n squared. That's z sigma over e squared. So e is the margin of error that we're looking for. That's the 10. We're looking for an e equals 10. So that's 368.30. We'll always round up. Round up of this value, and our answer is going to be going to be 369. Okay, so if we want to get a margin of error of not more than 10, then we have to go up from a sample size of 64 to a sample size of 369. Number 3. We have set of data. Local university an exam. We have 5 exam scores, and the scores are shown below. A, is it necessary to know anything about the shape of the distribution in order to make an interval estimate of the mean of all monthly incomes? The answer is, as we said before, here, since the sample size is small, we need to know that the original distribution was normally distributed. Why? Because that's what we need so that x bar will be normal. Okay, in order to solve anything, a hypothesis test or a confidence interval about x bar, we need to know that x bar is normally distributed. So again, as we said before, if the sample size is small, then we need to know that x is normally distributed. If the sample size is large, then we don't need to know that x is normally distributed. Find the standard error of the mean. So the standard error of the mean we've done a number of times. But now, since we do not know the standard deviation of the population, do not know sigma, so we have to find S in order to get the standard error of the mean. Okay, S is equal to now I can either write STDV or STDV dot S, because dot S is for a sample and this is a sample. Either one gives me the same answer, so you can write dot S or just STDV. And there's the standard deviation, but not of x bar. That's not the standard error. That's the standard deviation of x. Now the standard error is going to be, which is the standard deviation of x bar, is going to be S over the square root of n. S over the square root of n, and n is 5. Alright, so the standard error has the same formula as when you had sigma. It was sigma over the square root of n. If you don't, then you're going to use S, which is the standard deviation of the population, and take S over the square root of n. Give a point estimate of the population mean. The point estimate of the population mean is always the sample mean. In other words, x bar. So that's equal to okay, so our point estimate is 77. Now construct 80 and 95 and 90% confidence intervals for the mean. Now, as compared to the previous case, since the standard deviation of the population is unknown, we're using S. We're using the standard deviation of the sample, using the standard error of using the standard deviation of the sample, using S, and therefore we have to use T. So we're going to be getting X, the margin of error is going to be equal to T times S over the square root of n. Right? That's very similar to the margin of error that we had before, but that was Z sigma over the square root of n. Now we have T S over the square root of n. So before I can do that, I have to calculate T. I have to know what T is. So T, we're going to take T inverse. Okay, now remember how this works. The probability that it wants is the probability 1 minus the confidence level. So if the confidence level is 80%, then it's going to be 0.2. Again, it's 1 minus the confidence level that you put into T inverse. It's the part that's in the sum of the two tails. So if it's the center is 80%, so the confidence level is 80%, so 0.20 or 0.2 or 20% goes in there, and degrees of freedom. Degrees of freedom is n minus 1, 1 less than the sample size. The sample size was 5, so that's 4. And here is T inverse, 1.53 for an 80% confidence interval. Okay, so now we can get the margin of error. The margin of error, let's call that E. So E, the margin of error, is going to be, we said, is T times S over the square root of n, which is 5. All right, there's the margin of error. And again, we could have gotten the margin of error directly from the standard error by just saying that it's t times the standard error. T, because it's the same calculation, obviously. T times the standard error. We got that same value. And therefore, the confidence interval is going to be the mean, x bar, minus the margin of error, 2 x bar plus the margin of error. Now, that's for an 80%. For a 90%, all we got to do is get a different value of e. So for a 90%, t is equal to t inv of 90%. So 1 minus 90% is 0.1, and again it's 4 degrees of freedom. Now, for 90%, is the confidence interval going to be larger or smaller? Obviously, the larger the confidence interval, the larger the confidence level for a given sample size, the confidence interval is going to have to be larger to get a larger level of confidence. If that's the case, then this t-value is going to be larger because we're multiplying it times the t-value. Let's see what we get, 2.13. And now we're going to do the same thing as what we did before. So that is, the margin of error is t times sigma over the square root of n, or the standard error, 14. And therefore, the confidence interval is 77 minus the margin of error to 77 plus margin of error. Question 4. A certain car is known to have fuel efficiency of 30 miles per gallon. Standard deviation is known to be 1.8 miles per gallon. The manufacturer claims that the rating of the new model has increased. 50 cars are tested and achieve an average of 30.5 miles per gallon. So we know that we have n equals 30. That's the sample size. We know that the standard deviation is known because the standard deviation of the population, that's very important. The standard deviation of the population is known. And the standard deviation of the population is known to be 1.8. All right, so first of all, we need to know that x bar is normally distributed to do any hypothesis test or confidence interval. Do we know that x bar is normally distributed? The answer is yes. Why? Because the sample size is 30. As long as the sample size is 30, we know that that x bar is normally distributed. If the sample size were less than 30, then we would need to know that x, the fuel efficiency ratings of the cars of x, is normally distributed. So we're okay. X bar is normally distributed here because n is large. Next, state the null and alternative hypotheses. So to know whether there or not there has been an increase, we said that if you want to show that there's an increase, then that goes into the alternate hypothesis. Again, whatever you are going to accept without showing the contrary, without proof to the contrary, is the null hypothesis. What you want to show, if you want to show that there's been a change, that change always goes into the alternate hypothesis. So, in this case, the null hypothesis is that there has not been an increase. that there has not been an increase. And what was it before? 30.5 miles per gallon. I'm sorry, the 30. And let me just come back to here. I misread that. 50 cars are tested, so the sample size is 50. What we said still holds because it's a large sample size. The alternate hypothesis is what he's trying to show. He's trying to show that there has been an increase. So this is going to be that there has been an increase, so that's greater than. Again, this is a crucial portion of the this is a crucial portion of setting up the hypotheses to get them right. The thing that you're trying to show has changed, that goes into the alternate hypothesis, and in this case he's trying to show that it changed to be above 30 miles per gallon. Now we got an X bar of 30.5. Okay, what's the p-value associated? So if we got an X bar of 30.5, let's look at the normal distribution again. I have X bar under the null hypothesis, I'm sorry, mu under the null hypothesis was 30. X bar is 30.5. And p, the p-value will always be the tail in the direction of the alternate hypothesis. It's the tail in the direction of the alternate hypothesis. In this case, the alternate hypothesis is greater than. It's to the right side. So the p-value is going to be the probability that the p-value is going to be the probability that X bar rather is greater than or equal to 30.5. So that's what we're looking for. The probability that X bar, since it's a greater than probability, so we have to take 1 minus. Remember always when you're looking at the normal distribution, you're looking for greater than, you're taking 1 minus. So it's 1 minus norm dist. The mean under the null hypothesis was 30. We got an X bar of 30.5, so this is 30.5. 30. Standard deviation. Standard deviation is 1.8, but of course since we're talking about X bar, it's 1.8 over the square root of the sample size. So there's our p-value. 0.025. That 0.0247, that represents the shaded in portion. That's our p-value. If alpha is 0.01, will you accept or reject the null hypothesis? Remember, we're always going to reject the null hypothesis. Reject H0. This is the crucial thing to remember. Reject H0 if p is less than, if p is less than p is less than alpha. Alright, so we reject if p is less than alpha. In our case, p is 0.02, alpha is 0.01. So since 0.02 0.0247 is greater than 0.01, right? Therefore, we do not reject H0. We cannot reject H0. What does this mean with respect to the car's MPG? Well, if we didn't reject the null hypothesis, that means the null hypothesis stands. We have not shown that the MPG increased from 30. Again, if we would have rejected the null hypothesis, we would have shown the alternate to be true, and that would have meant that it increased. So if our p-value was less than 0.01, we would have rejected the null hypothesis and have shown that the MPG increased. Since we're not rejecting the null hypothesis, we're going with that the MPG, the mean miles per gallon, remains 30 or less. Number 5. In Chapter 9, there's a web file called Golf Test. I downloaded the web file. There are the distance traveled by 50 golf balls. In order to stay within the standard set by the USGA, ball is supposed to travel an average of 292 yards. So we want to test, is it 92 yards or is it different from 292 yards, meaning not more, not less. So the null and the alternate hypotheses are going to be H0 HA. I'm going to just copy it to get the muse. And let's see. If they're saying that we're concerned that it not be less or more, meaning we're trying to test, is it different than 292? So it's going to be a two-tailed test. It's equal to 292 or not equal to 292. Again, why is it two-tailed? Because we're concerned that it not be more or less. So that's one way of saying that it's two-sided. Another way of saying it is if we want to check, is it 292 or is it different than 292? That would also mean that it's a two-tailed test. All right, so we have the null and the alternate hypotheses. Assuming that the standard deviation is known to be 12. Okay, so if sigma is known to be 12, n is 50, x bar (297.6). Since the standard deviation of the population is known, we're going to use Z. Again, when the standard deviation of population is known, we use Z. Standard deviation of the population is unknown, we use S, and then T. So, again, now, since the N is equal to 50, that's a large sample size, so we're in business. We don't have to know X bar is going to be normally distributed. We don't have to know that X is normally distributed. That being the case, we're ready to go. So, the margin of error is going to be Z sigma over the square root of N. What's the we're doing a hypothesis test. So we're doing a hypothesis test to see is it equal to 292. So the p-value. Let's look at the graph. The p-value. (292). We got 297.6. With a two-tailed test, and using the z or using the norm dist, you look at the smaller tail and then double it. A two-tailed test, you look at the smaller tail and then double it. So in this case, you're looking at the probability that you're greater than 297. And since it's greater than, we're going to have to take 1 minus, this is, we're calculating what's in that shaded tail. 1 minus norm dist, 297.6. 292 is the mean. The standard deviation, 12. But it's not 12, it's 12 over the square root of 50. So never make that mistake. And that's the part in the upper tail. That's the part in the upper tail. Since it's a two-tailed test, the p-value is going to be double that. And there is our p-value. So now, with that t-value, what does this say about golf balls? Since the p-value is well less than alpha, we didn't say what alpha is, but assuming, we said that we'll assume that alpha is 0.05 if we're not given anything. So assuming that alpha so we have p is less than alpha, and therefore reject H0, and therefore we have shown that the mean of the golf balls is not equal to 292. Right? We're rejecting the null hypothesis in favor of the alternate hypothesis, meaning that it's not 292. Now, assuming the standard deviation is unknown. So if the standard deviation is unknown, we're going to do the same thing, but we're going to find S, and S is the standard deviation of the sample. And again, I can either use STDV or .S. So there's S. Once I have S, now I'm going to use T. And I'm using T because the standard deviation is unknown. Now, if the standard deviation is unknown and I'm looking for the T value, so T dist, and we said that T, really there are a number of ways. You can either use T dist or T dot dist. We'll use T dot dist because T dot dist works very much in the same way that the the norm dist works, and that's why we're using this. So now, since we're doing T dot dist again, and since it's the above value, so we have to take 1 minus T dot dist, just like we took 1 minus again because it's the above value. T dot dist again works very much in the same way that norm dist works or that norm S dist works. But of course, now we're stuck, because what's the T value? What's the T value that we're going to plug in? So before I can get the P value, I have to calculate the value of T. So we're getting a step ahead of ourselves. I can't do that until I calculate the T value in the same way that I would calculate the Z value. So the T value is X bar. And when you calculate it, make sure you put it in the parentheses properly. X bar minus mu over S over the square root of N. And in our case, that's X bar. Again, remember to put in the parentheses properly. X bar That's our sample mean, minus mu is 292. That's our assumed mean, divided by the standard error, or s over the square root of n. S over the square root of n. Right, so there is our t value. Now that I have the t value, I can calculate the p. Again, so what did we start doing before? What we did with the norm dist. We're going to say 1 minus t dot dist. And now I have a t value. T, degrees of freedom, sample size is 50. The degrees of freedom is 49. And again, we're always going to do true, as in the case of the normal distribution. So that's the shaded in portion. That's the shaded in portion. But again, since it's a two-tailed test, I have to multiply it by 2, so the p-value ultimately is equal to 2 times that. And there's our p-value. Alright, if you notice the p-value, because it's a large sample size, the p-value is very close to what it was when I used the z. Now again, the answer is going to be the same as it was before. What's the p-value? What does this say about the golf balls? Same thing as before. Since exactly the same thing as before, I could just copy it. Again, p is less than alpha, therefore we're rejecting it 0, and therefore we have shown that it's not equal to 292. And finally, number 6, regression analysis. So the following school districts we have, for a number of school districts here, we have the average class size, the SAT score, and the percentage of students who attended a 4-year college. Now, we want to perform 2 simple linear regressions to forecast percent attendance. Once using average class size as the independent variable, and again using the average SAT score. So let's do that first, and then we're going to see which one is better. Again, the dependent variable in each case, the y variable, this is going to be the y variable, and that's the dependent variable, and we're going to try size as an independent variable x, and we're going to try SAT score as an independent variable x. So data analysis, and regression. Okay. The y range, that's easy. That's the percent attendance, and that's always going to stay the same. Now we said first try, what did we say? First try size as the independent variable. So first we're going to try size as the independent variable. The labels are in there. The output range, let's just put right below. And there we go. So there is our answer with size. And, you know, let me just, we don't need these just to make it, just to save the space. Okay. Now I'm going to do the same thing. That's with size. I'm going to do the same thing now with the independent variable being SAT scores. Okay. The y range stays the same because that's what we're trying to predict. We're trying to predict percent attendant. We're trying to estimate this percent attendance. That's the y value. The y value is always the thing that we're trying to estimate. But now we're looking at the SAT score as being the independent variable. Labels are still in there, and we're going to change the, we're going to put the result over here. So now we have the other one. Okay, so we've done both of them. We've done 2 regression analysis. Which one of these is better when used alone? Explain. All right. To see which one is better, we're going to look at which one is statistically significant overall. So, this one with size, assuming alpha is equal to 0.05, the first regression, the one using size as the independent variable, is not significant because the overall significance, or the overall p-value of the regression, is 0.12, which is greater than alpha, and therefore this regression is not significant. Let's look at the regression using SAT score. The regression using SAT score, the significance f, or the p-value associated with the regression, is 0.06, which is less than alpha. Therefore, our answer is that the regression using SAT is, well, let's capitalize that. Using SAT is why? Because p equals 0.006 is less than alpha, which is 0.05. The regression using size is not statistically significant because the p-value is 0.127, is greater than alpha, and therefore it's not statistically significant, and so therefore SAT is a better model. Alright, there's our answer to question A. Question B. Now use average class size and SAT score together as 2 independent variables to form multiple linear regression. How does it compare to your answer in A? Alright. Let's see. So we want to use both together. The y variable, the dependent variable, is the same. We're still trying to predict the same thing, but now the x variables are going to be both of them together. Remember that these two have to be contiguous. The two x variables, the 2 independent variables, have to be in contiguous columns in order to do this. The labels are still there, and let's put the output right underneath. So we'll put the output there, and now we have a multiple regression. Let's look at our answer here. It does appear to be significant, right? Okay, it's less than alpha. However, when we look at the individual p-values, we see that the p-value associated with SAT score is significant, but the p-value associated with size is not. and that's 0.616, is not. Remember, the p-value associated with the SAT score, let's just write that one down too, is 0.0307. 0.0307. Therefore, this is not an appropriate model. Why? Because not all independent variables are significant. All right, now, therefore, to answer our question was, how does this compare to your result A? It's not independent, and therefore the best model, thus the best model is the one that uses SAT score only. So this model is worse. Question C. Estimate the percentage of students that attended for if the class size is 20 and the average combined SAT score is 100. So we want to use our best model. And therefore we're using the model that we got in Part A, the one with SAT score alone. Why? Because the one in Part B is not appropriate, the multiple regression, because not all the independent variables were significant. If all the independent variables in the multiple regression were significant, and the overall was significant, the overall p-value significance of the regression was significant, then that one would be the better model. But in this case, the better model is the one with only SAT score, because we've shown that the class size is not significant. Therefore, we're going to use the model that we got, and that's this one with this model right here. The equation was y equals minus 53.59 plus 0.12 times the SAT score. That's the equation. The equation here is y, which is the percent going to college, is equal to minus, well, let's leave it here, minus y equals minus 53.59. That's the constant. Plus 0.1235 times the SAT score. The class size is not significant at all, and therefore in our calculation for Part C, we're going to say that our estimate of percent attending with SAT score equals 1,000 is equal to, we're going to plug it into that formula. So let's get this formula back. What was the formula? Here's the formula. Control. Whoops. Oh, I see. I was at the equal sign. Here's the formula. Let's get it again. And and therefore we're plugging in minus 53.59. I can either type it in or take it straight from there, plus 0.12 times 1,000. So here is our estimate, 69.90%. Now what's important to know, what's important to recognize is that size was shown not to be statistically significant, and therefore does not appear in the calculation. Okay, that's the whole thing. Good luck on the final exam, and if there are any questions, you're welcome to ask.